Today's daily code problem of the day is cousins in binary tree part 2, number 2641. For this problem, we're given the root of a binary tree, and we want to replace the value of each node in the tree with the sum of all of its cousin values. So if we have two nodes of a binary tree and they're cousins, it means they have the same depth, but they have different parent nodes. And we want to return the root of our new tree. So if we look at this example here, 5 is the root of our tree, 4 is its child, 9 is its child, and they're not cousins, they are siblings. But 4 has 2 children, 1 and 10, and 9 has 1 child, 7, making 1 and 10 cousins to 7, and 7 cousins to 1 and 10. Because of this, when we're updating our new tree, 5, the root, does not have a cousin, so it's just 0. 4 does not have a cousin, so it's 0. 9 does not have a cousin, so it's 0. And our 3 nodes at the bottom do have cousins, so they're going to be the sum of whatever their cousins are. So 7 doesn't have a sibling, so 1 and 10 turn into 7 and 7, and 7 turns into the sum of 10 plus 1, which is 11. So for this problem, we are going to use a breadth first search, meaning we're going to look at each layer of the tree, count up the entire sum of that layer, and then subtract the sum of the node and its siblings to then equal it to whatever the sum of the cousins are. So after that, we can return our new tree. Let's jump into the code here. So first thing we're going to do is we are going to call to a helper function called breadth first search. We're going to pass it our root, and then we're going to be able to return that root as we're just going to modify our tree. So in our helper function, we're going to use a breadth first search. Let's go ahead and define that function. So we're going to have a private void breadth first search, and it will be passed a tree node called root. So for our breadth first search, we're going to use a queue to keep track of all the nodes on that layer. So we're going to have a queue. It's going to store tree nodes. And we can call this our queue, and it's going to be equal to a new linked list. Now we're going to add our root to our queue, so queue.add root. And that's just initializing our queue, and then we will initialize. So after initializing our queue with our root, we're now going to initialize the root's value to 0, because there's no possible way it can have a cousin. So root.val will now be equal to 0. After that, we're going to have a process where we're going to look at each node in our queue, and while we still have nodes in our queue, we are going to check to analyze if they have cousins or if they have siblings, and use that information to make changes to their sums. After that, we will add their children to our queue and progressively go through each node in our tree. So to initialize this and go through each thing in our queue, or basically through every single node, we're going to have a while loop. So while our queue is not empty, this while loop will continue. We'll get the size of our queue. We will get the level, we'll initialize the level sum to 0, and then we'll make a list of tree nodes, and this is going to be our current level nodes. And that will be a new array list. We're now going to traverse all the nodes at each level by using a for loop, and this for loop will add the nodes to our current level list, where we will then be able to make our manipulations. So for integer I is equal to 0, as long as I is less than our size, I will increment, and we will use a temporary tree node to get whatever is at the top of our queue. We will then add that to our current level nodes dot add our node, and now we can add any children from this node to the queue and calculate the sum of the current levels nodes. So if node.left is not not equal to null q.add node.left. If node.right is not equal to null, I'll get there eventually, q.add node.right. So now that we're looking at this node, we'll add its children to our queue so we can process them later. And now we're going to calculate the sum of the current level's nodes. So if node.left is not equal to null, level sum plus equal node.left.val. If node.right is also not equal to null, then our level sum will plus equal node.right.val. It's as simple as that. So after this for loop is going to add the children to the queue, add their sums to the level sum. We will now replace each node's value with the sum of its cousins. So for tree node in our list current level nodes, we are going to initiate a sibling sum. So we have our level sum, and now we're going to have a sibling sum. So int sibling sum. And we're going to use a sibling sum to subtract from our level sum. So if a node shares a parent with another node, we will subtract those two values from the level sum, and whatever's left over will be the node's new value. So if node.left is not equal to null, our sibling sum will plus equal node.left.val. Otherwise, additionally, if node.right is not equal to null, our sibling sum will plus equal node.right.val. It's as simple as that. So now the node's new value is the level sum minus its sibling sum. So we're going to update our children's sums. If node.left is not equal to null, again, it'll be node.left.val is equal to level sum minus sibling sum. And if node.right is not equal to null, node.right.val will be equal to level sum minus sibling sum. And that's it for our breadth first search. So, using this, we traverse the tree from top to bottom. This is not a normal search where we go bottom, middle, top. We go from top to bottom. So first we look at 5, and then we look at 4, 9, and then we look at 1, 10, 7. But we look at it as we update their children. So when we're looking at 5, we update 4, 9. When we look at 4, we update 1 and 10. When we look at 9, we update 7, if that makes sense. So our breadth first search travel, we use a queue to traverse our tree level by level, and each time we complete and process a level, we know all the nodes of that level. While we're tracking the level sum, we just calculate that by adding all of the sum of the nodes on that current level, and we store it in a list. We then use our cousin sum calculation by subtracting sibling sum from level sum, and then we replace the node values. So if we run this, passes our test cases, and if we submit it, it passes all solutions. Thank you, and follow for more daily LeetCode solutions.